Okay, good morning and afternoon to folks on the East Coast. It is wonderful to be here and to talk about Lunar Trailblazer. So Lunar Trailblazer is a small sat mission. So this is a mission that costs about 1/10 of what a typical discovery mission costs. So we're trying to pack a lot of science to follow up on important discoveries into a relatively small package. So I'm going to talk through the mission goals and objectives, and then also kind of bring you up to date to where we are on the status of the mission. I mentioned it was small. It's about 200 kilograms, basically, for the entire spacecraft, and it fits into an ESPA Grande ring space. And it has an incredibly capable payload, which follow up and build on the Moon Mineralogy Mapper, which flew in 2009 to the moon and gave us amazing data that I'll talk about shortly, and the Lunar Thermal Mapper, which is being built at Oxford and builds on Diviner. So we're basically making the next steps at a higher resolution, a better fidelity to follow up on a lot of very exciting discoveries. So the data that are shown here are from the Moon Mineralogy Mapper, and I know Noah talked a lot about the LRO results and everything that we've learned from LRO over the last decade. But these are the data that we have that really were able to map on a global scale the distribution of hydroxyl on the lunar surface. And this was not something when we built the instrument that we expected to find. We expected to maybe find something in the poles, in the permanently shaded regions, but we really didn't expect to see this signature on the illuminated surface. And, you know, it's still recent to me because I was finishing grad school, but looking back at this and thinking about how much has changed over this last decade as we worked with this and looked at observations from aircraft, from other flybys of the moon, and really dug into this. I think it's really been a paradigm shift in what we know about the moon. So, but what we would like to do is follow up with instruments that are specifically designed to look at this time on some key targeted areas to understand how are the volatile compounds distributed, how do they move across the surface? Are they moving across the surface? What are they associated with? And this also feeds into the exploration, obviously, because it helps us to understand what is the nature of how this is distributed in the lunar regolith, both laterally and kind of on a grain scale type level. And then with the thermal mapper, we can understand the thermophysical properties, which also go into understanding the character of these deposits, as well as potentially their extractability for the future. So, you know, the PSRs are obviously a very large target for science and exploration. We have evidence from M³ and from other instruments that there is ice, at least mixed at some level in some of these PSRs, but there's a lot of questions about it. Where is it specifically? Where is it in the permanently shadowed regions? Where is it around the permanently shadowed regions? And we're going to be able to really follow up on this and look at the distribution of ice as well as any molecular water that is intermixed with the regolith in the polar regions. Also across the lunar surface, we're going to be looking at both this illuminated region close to the poles, but across the entire surface of the moon to try to distinguish whether we're looking at hydroxyl bound in the regolith, whether we're looking at water in the regolith, perhaps in agglutinates, or if we're looking at some kind of more transient process that's mobile across the lunar surface. And I will go through that in more detail shortly. The other thing we'll be looking at, because we span the entire spectral range that M³ spanned and more, we'll be able to map this with the lithology under where we see the signatures of hydroxyl water and understand whether it's preferentially associated with certain lithologies and potentially whether some of this may be indigenous to the lunar surface rather than something that's formed through solar wind processes. So the goals and objectives are to determine the form, abundance, and distribution of water and OH across targeted regions on the lunar surface, test for any temporal variations, understand the form and abundance of ice and other water species at the poles, and then understand how gradients in the albedo and surface temperature affect both the concentration and the migration of water on the lunar surface. All right, so digging into what we're getting as far as the character of the data. So we'll be collecting with 2 push-broom instruments these image cubes of the lunar surface. They're going to be small, well, small compared to M³, which has noodles like pole-to-pole noodles. So we're looking at targeted regions that are about 20 kilometers by 20 kilometers across. And embedded in that, so that's the near infrared data cube. And then embedded in that is a thermal data cube that gives us information both about the temperature of the surface, but also about the composition, the silicic composition of the surface. So what we're doing that really builds on M cubed is looking to a longer wavelength, looking with a higher spectral resolution, as well as a higher spatial resolution. So we'll be able to distinguish the different species in some of these more finer scale or higher frequency spectral shape of the bands. This also means, because we're going out past 3 microns, all the way to 3.6, we'll be able to understand whether there's organics or other materials that are intermixed with the deposits that we're looking at on the lunar surface. Now, our operations scheme have us looking at the same spot multiple times throughout the day to monitor whether there are changes. We have designed observations where we'll look at latitudinal strips to understand how it varies as a function of latitude, but we're not going to image the entire moon like we did with M cubed. So we have to be very careful, especially with such a small, a nimble, agile, but inexpensive spacecraft. We have to be very targeted and strategic in how we're collecting these data. So we will be able to distinguish at the poles between water and lunar ice. That's kind of shown here. And I'm assuming I'm running close to out of time, so I'm going to hustle a little bit. Moving on to the spacecraft configuration. As I mentioned earlier, we fit in an Espegrande volume. And to give you an idea of like human-sized what this is, here is our PI, Bethany Ellman, next to a model of this. So, it's tiny. It's like a European refrigerator, maybe. It's probably bigger than that, but now, like I said, we have a target deck basically of, I think we have 2,000 images in there right now, but the nominal plan is to collect 1,000 targeted images. Some of these are required to be retargeted throughout the lunar day. Some of these we can image just once. And we'll be collecting these as we orbit in our polar orbit over the course of the lunar day.
3 minutes.
All right. Whew, thank you. Thank you for doing 3 minutes and not 2 minutes. All right. So another way that we really can make this possible is that we're leveraging a lot of work from students, both from Caltech, where Bethany is located, as well as Pasadena City College. And as a community college graduate myself, I'm like super excited to see that we're bringing in a lot of work. And we have students that are doing modeling of the time of day that we want to image the PSRs to get the best possible signature. We have students that have been helping out with the website and understanding, like trying to help the public visualize some of the issues with respect to lunar water, as well as helping out with the scheduling software and whatnot. So they're really embedded in the mission, and I'm very excited about that. So one current status, we are basically on our way to a delivery in early 2023. We were originally planning to launch with IMAP in late 2024, early 2025. But the day after my birthday this year, we got the wonderful news that we are going to be on a rideshare with CLPS. And right now we're looking at 2023, middle of 2023 launch. So we will get to the moon, depending on exactly when we launch, or we have some amount of crews, and then a 1-year nominal science mapping plan to achieve all of our exciting science. So here's just some images. We have like actual hardware, which is super exciting. Here are some of these that are being built and tested right now. And I'll just leave it here. I think we're going to do a lot of really amazing science, and I invite you to come see our beautiful website that the students have helped with. And feel free to talk to me if you want stickers or want to talk about Lunar Trailblazer later. Thanks.